So if there's friction, then the work done, you have to deduct from that. Deduct the work done against friction. But in this case, we assume that there's no friction first. Later on, we introduce friction. In our problem, we introduce friction. So now, uh, the work done in stretching the spring or compressing the spring. So it can be both ways. You can push the spring and compress it, or you pull the spring you pull the spring by stretching it. So there are two words: compression and stretching, two words. Okay. So either of these case also we use the same formula, half kx squared. Okay. So sometimes you may not start from the equilibrium position, from the zero position here. You may start from a certain compression and you compress it further. So between two compressed state, it is not between the equilibrium state and the compressed state. Sometimes it is between two compressed state. So if you want to know the work done between two compressed state, from one compressed position to another compressed position, then you should use this formula. The work done is half k x squared. The first x is the final position of the block, minus half kx squared. The second x is the initial position of the block. So you use the energy at the final position minus the energy at the initial position, and that will be the amount of energy used to move from one compressed state to another compressed state. Okay, so because this is the work done, and we know from the work energy theorem that they are related to one another, they can be transferred from one to another. So we say that the elastic potential energy is denoted by PE. PE means the elastic potential energy, and there's a small s at the bottom there. The small s means the spring. So elastic and potential energy stored in the spring. Now, if you compare with the other elastic potential energy, there's a PE G. The G one is the gravitational potential energy. This one is the spring potential energy, right? The gravitational potential energy is, the formula is different, right? The gravitational potential energy is mgy, right? This one is not mgy, this is half kx squared. So half kx squared is the potential energy of the spring. The other potential energy with a small g at the bottom there is the gravitational potential energy. Okay, so far what we have seen is work done against the spring or work done by the spring. They are the same, right? Equivalent, or is half kx squared. And if we include this spring factor in our conservation of energy equation, it will be something like this, right? So in our energy equation or the work energy theorem, we have the kinetic energy, gravitational potential energy. Now, after learning this spring potential energy, so we include one more factor here, the spring potential energy, right? So these three, they are intertransferable. They can be transferred from one form to another. This conservation of energy, if we rewrite this equation, it will be, you see the I there, the small I here denotes the initial kinetic energy, initial gravitational potential energy, plus the initial potential energy in the spring. So we have the total initial energy, and this will be equal to the final total energy. The final total energy also has three: final kinetic energy, final gravitational potential energy, and final spring potential energy. So this problem is different from our previous one. Our previous one, we have only two factors. Where is it? Here. We have only two factors here. Only kinetic energy and gravitational potential energy. But now we have three. Right? We have three. Total energy in before and the total energy after, they are equal. Any questions so far?
No questions, sir.
No question, then we are going to dissect them into small parts and try to understand them. So these short questions here will help us to understand the spring potential energy. Right? You read the first question, 5.5.
Calculate the elastic potential energy of spring with spring constant K equal 225 Newton per meter, that is A compressed and B stretched by 1 meter times 10 to the power of negative.
Okay, so now there is a spring, and this spring has a spring constant K of value 225 Newton per meter. That means if you are going to stretch it by 1 meter, you need to use 225 newtons. So this is the spring constant. We are going to calculate how much elastic potential energy is stored inside the spring when you compress the spring by 10 to the power minus 2 meters. Or how, and in the second case, how much energy is stored when you stretch the spring by 10 to the power minus 2 meters. So there are two parts here, two questions. First question is, if you compress the spring, how much is the energy? If you stretch the spring by the same distance, how much is the energy? Given the spring constant is 225. So we are going to use the formula like this. Potential energy, or the potential energies for the spring, is half kx squared. K is the spring constant, so we replace the k with 225. X is the displacement, or the distance from the equilibrium position, and that is 10 to the power of minus 2. But they say x squared, so it's 10 to the power minus 2 squared. So using your calculator, when you calculate this number, the answer is 1.13 times 10 to the power of minus 2 joule. Okay. So this one is for compressing the spring. In the second case, we are going to stretch the spring, and we are going to stretch it by the same distance. Earlier on we compressed, now we stretched. We still use the same formula, half kx squared. So half k is 225, and the distance from the equilibrium position is also 10 to the power minus 2. But even if this displacement is a negative number, when you square it, it will become positive, right? So it doesn't matter whether you push it to the left or you pull it to the right. When you square the displacement, we know displacement is a vector quantity. It has a positive or negative value. But when you square it, all become positive, right? So when it become positive, they are the same number, 1.13 times 10 to the power of minus 2 joule. So whether you compress or you stretch the spring, as long as the distance moved, the displacement is the same magnitude, the same amount of energy is used, or the same amount of energy is stored inside the spring. Okay, so this is the first thing we know about the potential energy in the spring. Okay, you read the second question, quiz 5.6.
True or false? The elastic potential energy of a stretch or compressed spring is always positive.
So the answer is
True.
true, because energy is a scalar quantity. Energy has no direction. If that is the amount of energy you put in, whether you put in, there's no such thing as I put in the energy from the left, I put in energy from the right. No such thing, right? Energy is just a scalar quantity. Okay, so true, right? That's true. Okay, you read the next part, question 5.7.
Elastic potential energy depends on spring constant and the distance the spring is stretched or compressed. By what factor does the elastic potential energy change if the spring stretch is A doubled or B tripled?
Okay, so now what they are trying to say is, let's say if I stretch the spring over a distance of x, okay, this has a certain amount of energy. Or let's say I do the same thing, but this time I stretch it over a distance of 2x instead of x. So I'm doubling the distance moved. I'm doubling the displacement, the stretching of the spring. So in what way is the energy in the second case related to the energy in the first case? So we're going to use calculation to show the relationship. Okay, so let's say the first case, we are moving it over a distance of x. We are stretching it over a distance of x. So it will be half kx squared. Fine. Now in the a there, when it is double, so when it is double, so we have half k instead of x. Now we have double 2x. We stretch it over a distance of 2x. So what will happen when you square the 2x? You square the 2, it becomes 4. You square the x is still x squared. So it will be 4 multiplied with the original half kx squared. So what can you say about the energy? How many times? What is the
Uh,
factor? Because you square the 2, it will become 4. So you will not have a factor of 2, but you will have a factor of 4. So it will be 4 times the original amount of energy used. Earlier it is half kx squared. Earlier it is half kx squared. Oh, now because of the 2 square here, it becomes 4 multiplied by half kx squared. So the energy is 4 times. Part B. By what factor does the elastic potential energy change if the spring is stretched triple. Triple means 3 times. So of course, initially it will be half kx squared. When the distance is stretched 3 times, instead of writing x squared, we will have 3x squared. We will have 3x squared here. We have 3x squared. So when you square the 3, it becomes 9. When you square the x, it is still x squared. So you move the 9 outside. Move the 9 outside. It will be half k x squared. So it will be 9 into half kx squared. So can you tell me how many times is the energy? When
9 times.
9 times. When the spring, when the distance is 3 times, the energy used is 9 times. 9 times. So this is the sort of relationship that we can see. This is the thing that we need to know about elastic potential energy. So it only depends on the distance moved from the equilibrium position, and the energy is not linear. The force is linear, right? The force is linear. We've got kx, but the energy is kx squared. Is quadratic, right? It is quadratic. It is square. Square